All right, let's consider an example when an object sinks and therefore has apparent weight. So right here you have an object, we don't know what it's made of, what the density is, and what the size of it is either. We know for sure that it has actual weight of 45 newtons and apparent weight of 35 newtons, and it's an oil. So oils have different densities, and you will be given the density of this particular oil in which this object was weighed. So since this object has apparent weight, that means that it sank. Because how do you figure out apparent weight? If we measure the actual weight, we can use the spring scale, and it will tell us how much the object weighs because it basically measures the force of gravity. If, however, we place the same object into some kind of fluid, we will have two forces working against each other. So we will have the mg going down, which will be the actual weight, but we will also have some buoyant force, which will make the reading right here less. That's why it's called apparent weight, and we dub it as mga. So in this case, you have this equal 45 newtons, and that equal 35 newtons. That's the apparent weight. Alright, so here's all our data. We have the actual weight of 45 newtons, apparent weight of 35 newtons. This is the density of the fluid, which is oil. Our question is, find the density of the object itself. You know, the formula for density is mass over volume. Since the object sinks, if you were to draw the picture, since we're measuring the apparent weight, the whole thing is in. So the volume of the object equals the volume of the displaced fluid. So there we go. Alright, buoyant force, according to Archimedes, is density of the fluid times volume of the fluid, which is mass of the fluid times g. So remember, buoyant force equals the weight of the displaced fluid, so that's mass of the fluid times g. Apparent weight is the difference between the actual weight and buoyant force. So what I'm doing here is I can rewrite from this formula for buoyant force. I can say that the volume of the fluid from here is buoyant force divided by density of the fluid times g. And that is exactly what I have here. So then buoyant force is the difference between mg, which is the actual weight, and apparent weight. In our case, it's 45 minus 35, which is 10. So this right here is buoyant force, which is 10 newtons. This right here is, if I remember correctly, 802, and that is 9.8. So the volume of the displaced fluid can be found as buoyant force over density of the fluid times g. Buoyant force is the difference between actual and apparent weight. And then we put all the numbers in and we get 0.12 meters cubed. That is the volume of the displaced fluid, which is the volume of our object. So therefore, we can take this volume and put it into the formula for density. Density requires us to have mass over volume. Mass can be found as actual weight over 9.8. So we end up having 38 kilograms over meters cubed as our density of the object. Here's a third example. That's a critical thinking example. That would be something that you can find on a quiz or a test or a final. In this case, I'm asking you to compare the density, not the density, I'm sorry, the buoyant force on two objects that have identical mass of 350 grams. One object is copper, so it's a solid, some kind of, I don't know what kind of geometric figure it is, but it's just a sample of copper, solid copper, that has a mass of 350 grams. And then we have a solid chunk of ice that has the same mass, 350 grams. And your task is to compare the buoyant force. The natural thinking is Well, copper is heavier, so therefore it will have greater buoyant force. But that's a trick question, because copper will definitely sink. So the whole thing will be in H2O, in water. Ice, however, will only be partially in water. So the entire amount of ice is not going to displace the entire amount of water. So that's one way of thinking. But then the same thing, look, the way I drew this is incorrect, because obviously 350 grams of ice at that density is going to be greater than 350 grams of copper, which has this density. So we'll probably have this amount of ice and this amount of copper. Alright, so as you start thinking more about this, you probably will get to the idea that copper will have less volume and therefore displace less fluid. Well, anyway, let's figure out it with numbers. Ice will float, copper will sink. So therefore, how do I find the buoyancy, the buoyant force on ice? That will be the weight of ice. And the weight of ice is the mass, which is 350 grams, needs to be in kilograms. Oh, this is actually extra. So 0.35 times 9.8, so it's 3.4 newtons. That's the force of buoyancy, which also equals the weight of the ice. Now, with copper, it's going to be different. With copper, since copper is not floating, buoyant force can only be found by Archimedes' principle. So therefore, I'm saying that it's going to be mass of the fluid times g. Mass of the fluid is density of the fluid times volume of the fluid. The entire thing is going to be in water. So the volume of the fluid, again, equals the volume of the object. So buoyant force on copper is going to be the volume of, the density of water in the volume of copper times g. So then I'm taking the mass of copper can be, that's kilograms, right? 350 grams is 0.35 kilograms. Density of copper I gave you, 8,890. So I end up with 3.910 to the negative fifth. That is how I find the volume of copper, because that's the mass of copper over density. That's how I find this right here, because that's the only thing that we didn't know so far. So from there, the buoyancy force equals the density of the fluid, which is water in this case. This is the volume of the fluid, which is also the volume of the object, and that's 9.8, and we get 0.38 newtons, which is in fact is less than 3.4 newtons on ice. So even though copper is heavier and more dense than ice, it still has less buoyant force on it because the volume of it is small. Obviously, if we had a greater chunk of copper and its mass would be huger than mass of ice, we would have a different case. For example, if we had the same amount of ice and the same amount of copper, speaking volume-wise, then of course, because the entire volume of copper would be underwater, the buoyant force on it would be greater than the buoyant force of ice of the same size. But if we're talking about mass, that is equal. We had mass of copper equal the mass of ice. In that case, obviously, here was copper and that was ice. The buoyant force on this is greater than the buoyant force on the small piece of copper. There you go.